Okay, so to sum up this part, I want to do a full video about the proof of the Olivo-Schumacher-Westmoreland theorem. So yeah, to recapitulate, the goal of this theorem is just to find the capacity of classical communication that the quantum channel can send. So it's just like the maximal debit, like the maximum number of bits by utilization of the channel that Alice can send to Bob with a probability of error which is really small. So basically you have Alice, you have Bob, you have some bits that encode the information. You want to know how many bits you can send using this quantum channel. And so the result is this oligoregularity information. So this capacity of communication is just the Olivo information. Olivo regularity. So to prove it, we need to prove two parts, the direct part and the indirect part. So the direct parts, it's just like to prove that all rates is achievable. Like no matter what Alice sends, Bob can recuperate everything, and the part 2 will be just to say that it is impossible to the bus to be bigger than Olivo, than the regress Olivo information. So basically, if there is like zero error, if it's not possible because there is always a little bit of noise, so not bigger than x-ray. So yeah, basically just in more formal terms to say that part 1 says we can send everything with a very low probability of error, and here is like there is always be normally very little error, like the regularization of information uh, being normally a little bit superior to zero, like, because the code cannot work without errors. I mean, you want to try to minimize error, but yeah, it will exist. So let's prove this part 1, where we try to find that no matter the number of message that Alice can send, then Bob can decode without error received, like n, which is the number of bits that will encode the information, number of qubits that will encode this critical information. So yeah. So basically, if I made it more accurately, you have the Alice that sends his stuff through the encoder, and after through the content channel, and after through the decoder, and so after there is Bob. And so here we select some typical states. So for example, um, like you just see like you have some typical states that appear most of the time, so you take them to represent everything. So the consumption it creates noise, and after you do the pretty good measurements with Bob on the typical space where there is this typical states to recover the states that were sent initially by Alice. And so this typical space and typical state, just consider this as typical sequences that we can find. Like instead of considering all type of messages, you consider just the most representing of them, as I said. Um, yeah. So let's go through it. Let's prove first, for doing it, that we have the right to restrict ourselves to the typical space. The equation we have is this one. The sense of this equation is that the probability of going onto a typical sequence is like less or more equal to 100%, 1 minus epsilon, epsilon being very small. Like atypical sequences are so rare that we can ignore them. It's just like you have a piece, you flip it 1,000 times, and so an atypical sequence will have 1,000 head or 1,000 tail, so you can eliminate them because most of the time would be have 500 head and 500 tail. So that's the first step. The second step, so thanks to this equation, we understand that it's alright to take a typical subspace. The second step is like to have some bounds on the truncated state and its dimension. So here is the equations. Um, what you sense about it is that the state that is restrained to the typical sigma is not really different from the average one of the global state. So yeah, if you're in the typical state or in the typical subspace and in the global space, there will not be a lot of difference because it's just 1 minus epsilon to the power of minus 1. And for the second equation, you just understand that the operation of the typical projection cuts everything that go out of it. So the dimension of this typical space of reception just like borne by the entropy of von Neumann. It's just like you have cards, on a table, and you just say, well, I want my table to be a little less bigger, so I'm sure that uh, everything will be alright inside of it, and that your cards also on the tables, you take them a little bigger. So because you take them a little bigger, like you're sure, like you're not missing information, and the table is like um, a little less big, so you're sure you're not overriding your space. So yeah, this way you do not override your space. And that's it. That's our second step. Our third step is just the packing lemma, and so the equation about it is this one. It just applies POVM for the channel. Select simple to epsilon plus 2. Minus C plus C prime epsilon. And so you see like the C prime epsilon, just like what I explained, like where we have this explanation about it, about the skirt on this table. So the sense of this equation is like P star is just the worst probability of error of decoding I think all the messages, and the error is like cut between the typical noise, which is this, that the messages are overwriting one of each other. That's why we take the cards, on the table. We take a little bit more, so we are sure they do not override. And so that's the goal of the packing lemma, making them not override from being sure they are not orthogonal one to each other. And so the first step, no, I did not. Oh, okay. I thought it was the end of the video, but it seems alright. The first step uh, is like to choose the number of messages. Okay. So if I sum up, like here, we prove we can restrain to a typical subspace. Like it does not change really something. Here we just like make sure the space is okay. Here we make sure the message inside of it not override on one each other. And finally, because now we know all of this, we can like choose a number of messages we can send, because we just seen that we were able to restrict ourselves to a typical subspace, and that we can put our stuff non-orthogonally, and we just need to choose about it. How many? So if we choose m, the number of messages including 2 to the power of n of I xb minus c plus c prime plus 1 of epsilon. So that's our equation. So just p is the 4 of epsilon plus 2, 16 of 1 minus epsilon plus 1, 2 minus sigma. Then we can see that the rate of communication is 1 over n log m, which is like just noisy information without its merge. So by injecting m into the bourne of error, the information, the mutual information, can cancel itself. So to just have this anymore, because we will have one, and so it will be conserved. And so when n is equal to infinity, then this will go to 0, and so the error of transmission will be equal to 0. So yeah, we just proved that you'll just have, no matter what, no matter if you choose the right number of messages, like you can send whatever you want. If you take n going to infinity, and the error of transmission will be equal to 0. And if you extend this to n XOR k, like multiple sendings through the channel, you achieve Olivo information regularized. So that's the part 1, directions. So we need to prove now the converse that we cannot go over Olivo information. Like the rate will be always inferior. So you have your message M as before, the encoding, the channel, the pretty good measurement with the POVM, and M prime with Alice and Bob. So the same process. And so the mathematical tool that we will be used will be the perfect state that we try to find, where the ideal state of Alice is exactly like the state at the beginning and the state of the end are the same. We will be also using the continuity of the inequality of Ali Keith and S. Winter, which says that if we have a theorem that says that two states are near from each other in the norm trait, the mutual information are close to one each other, So just say like um, trace neuron and entropy input formation material information are close to each other. Like it implies like the trace neuron is close, the entropy of the material information is close to for two states. The data processing inequalities that say that if you measure something, like you will not increase the information. That's basic. Measurement and create information. Oliver bounds that say that the maximal information that we can extract of a quantum classical states. Uh, so yeah, just the max of info by def, you know. So just by def, in a way, we can say that cannot override it. Yeah. So let's go now through the equation. So first we want to do is modelize the experiments. So the experiment is this one. We just sum over all possible messages when we see of 1M and just all the messages. So trace of the POVM of Bob with the channel on the state of Alice. Um, with the state of with the two classical states, So that's what we want to check about. And so we saw here that WM prime is a real confirmation matrix between the real message M of Alice, um, the guess of Bob, and so we have also that the real, like the ideal states minus the real states is inferred to epsilon, saying in a way that Bob can never really be wrong, like most of the time, or really few wrong, so can ignore it. And so the second equation just the major chain inequality, which is this one. Where we basically like prove something about just the information on Natalevo directly, so to use it just after. So at the beginning, here it just uh, ideal stuff, because in the perfect case that errors the quantity of information that is shared between the message sent by by Alice and received by Bob is like 100% of the message. So ideal case, perfect sense, and so it's just equal to log of m bits. And so after there is here the real noise, because in reality uh, our W stuff is not our psi stuff. Like W is inferior to psi. Like how to say now? C is inferior to W because with W has a noise. The continuity IFW just says that meter information cannot be a lot bigger than the ideal one. A lot. Uh, so yeah. So we just have here, the noise of the real life that is applied, and after we just have the data processing inequality, where we just say that we cannot create more information when we measure. Um, and after by definition that's by definition the maximum of information we can have is O level. So if we apply the mutual information by O level, it would be just superior to it. So yeah, no. By the way, here it's MM prime. Does not clear. Like, just say that the info after the measurements um, cannot be bigger in a way. Yeah. So yeah, basically we just applied like ideal case, and after the real noise, and after the measurements, the data processing inequality not increasing after the information. And so the step after is just to taking n to infinity. Um, so dividing all by n and rejecting c, we just find this. So divide all by n. We define c being minus 1/4n. And so the sense just to say like when the block go to infinity, the probability of error will go to 0. And so this will be equal to 1. This will be the binary step will be equal to 0. And this will tend to the regularized O-level information. And so we just see that we will have C, which is here, like this will be to 0, this to 0, so we will just have this. We will just have C, which will be, sorry, we will just have C, which is inferior to serialized O-level information. So yeah, if we sum up, like in the achievability sense, the direct sense, like um, we just proved that we can send less formal information by constructing a code of size 2 to the power of n of the information of xe, and checking that zero will cancel itself using the typical subspace on the packing lemma. And so we have this. And so in the converse sense, we just prove that we can go um, over it. So no matter the code will not go over a level bound uh, bounded by. And so for this, we just this. And so here we just use like packing lemma on typical subspace. And here we used IFW data processing inequality and the noise. And so thanks to both of them, we were able to have um, the HSW theorem, which says that the capacity of the channel we can the max the the capacity of the channel, the capacity of information we can send from Alice to Bob going from a quantum theorem is exactly equal to the regular audio information. Thanks.